So Dave, I have an idea, and I know it's a bad idea, but I'm going to tell you my idea anyways.
Okay.
So I have a pipe, and what's a lot of flow for something like this?
100 CFM in a 1-inch line.
Okay, so I got 500 CFM,
Okay.
and my boss says I need to save money, so I'm going to take my 5-inch line and I'm going to put it down to 1 inch, and I'm going to run it through this. And I think I'm a genius because I'm saving money.
Yeah.
So what happens if we start trying to run too much flow? Essentially, what happens if we choose the wrong size?
Yeah.
I'm assuming if we have
So let's say you now want to put 5 times the amount of flow through this pipe because you have the sufficient energy to push that flow through that pipe, and the energy that you use to push that flow, it costs you nothing and you don't care, so you want to just make a cheaper flow meter.
my boss says they're too expensive,
Yeah.
choose a cheaper flow meter.
So if you have a vortex meter, the vortex meter doesn't like to go too high, but this thing can go to like 100,000 feet per minute. It's an unbelievable machine. The thermal flow meter would be fine with that.
So we're just going to get a bigger temperature gradient here, and you're like, no big deal.
Yeah, we don't care.
Maybe there's going to be less accuracy?
No, if we characterize it in that pipe with this system for your gas, we can characterize it to the level of uncertainty of our calibration equipment. So this R&D system here is a closed loop wind tunnel, I call it, but it's a calibration system that has 1-inch and 2-inch pipes using Roots meters as the standard, the transfer standard. Roots meters are considered billing meters. You'll see them outside of In-N-Out Burger, spinning away. And what they do is we run the gas through them. It spins a little turbine, a really well-designed
Turbine meter, basically.
Well, it's not a turbine. It's lobes, like a what do you call it in a car? Blower. What do you call a blower in a car?
You're talking about turbo?
Yeah, the supercharger in a car hooked
Okay.
up to the
Yeah, it spins
fan
around.
wheel.
Yeah. Okay.
That's what this thing is. It's a blower. It's a pump, but in a passive way, with very low friction. It counts how many pulses per rev, and there's almost zero leakage between the lobes, and we count the frequency of this device, and we turn that into 1 liter, 2 liter, 3 liter, 4 liter, 4, 5 liter.
It's just a counter.
So it's a counter, and it represents itself on this. There's hundreds of ways to do it. This is the way we do it here.
Okay, so let's talk about this then. Right now we have a turbine meter.
Now we have a Roots blower,
A Roots blower.
Roots meter,
Okay.
a Roots meter in series with a blower.
Okay.
So the blower is this is from, what's that company called? Blacklight Power or whatever.
Okay.
Can't remember. Anyway, a company who made hydrogen things who failed in the valley. So we bought their
We bought them.
their explosion-proof blower and hooked it up to that Roots meter and just made a little loop where the flow goes around and around in circles.
And then you're writing LabVIEW software here.
Yeah, LabVIEW's one way, and I'm comfortable with LabVIEW. I can write something in LabVIEW.
Dave just kind of picked up LabVIEW when he was kind of bored of designing flow meters, and he thought, why not?
A necessary evil of making flow meters. You need to characterize them well. So we have, this is NIST traceable. We have a temperature, a pressure, a barometer, a room temperature. We've characterized the RPM to flow rate using a Bell prover, and then we can instantaneously measure the flow. We drive the blower with this little VFD, and I'll turn it a little so you can hear.
So what do you do right now? You just turned on the flow read.
I'm driving a VFD, a variable frequency drive blower to spin everything. This kind of noise is like
So all of a sudden we're getting more
yeah,
flow
more flow.
through the pipe.
So
yeah,
what?
turn it down again.
Yeah.
That's cool. Already I'm pretty impressed here. And I want to kind of back up and understand what we're doing right here. And it sounded like in this there was a bunch of errors, stuff like that, and we had to figure out how to get rid of the error, and it was kind of like magic. I feel like this is the magic. Is that
That's
accurate?
right. So what we do is we create a condition of flow with this. This says it's 1 CFM. We believe this because NIST tells us.
Okay, so just to back up, we have a really accurate, expensive system here.
Yeah.
That's completely accurate. We know it's accurate. And then we have our flow meter, which doesn't cost $300,000.
That's right.
So not quite as accurate.
We are now characterizing this
And
with
is,
that.
is this the one that's set up right now?
Yeah.
Perfect. So that was a good example then. So what we've done is we're measuring the error between this reading and our 100% accurate reading, and we're using software here to describe that relationship.
Yeah, that's the back end, which most people don't.
I think that's kind of interesting.
Yeah, it's cool, but it's a.
I'm just going to zoom in and show the back end here. So for the viewers,
LabVIEW is
this is
a
the back end.
graphical programming language that is extraordinarily well done. As an original C programmer, this was the worst language in the world. For me, it was a threat. And how could they insult me by drawing pictures instead of me using, text to describe things? But this is an extremely efficient program that has the ability to talk to almost any device. They've got dynamic link libraries to all kinds of I/O, A to Ds, D to As, frequency, everything.
And basically what Dave's doing here is figuring out where the values from the expensive system and his system diverge, and creating an algorithm to get rid of that.
Well, what the person who buys a flow meter, they'll get actual flow, indicated flow, actual indicated, and what we'll have actual indicated, we will take those values, the actual flow, and the indicated will be frequency in this thing. So it's 1 liter, it's 10 hertz, 2 liters, 20 hertz, 3 liters, 40 hertz, 4 liters, 52 hertz, some weird number, 5 liters, 74, whatever it is, is a representation of hertz versus liters. We then characterize that, and in the vortex meter, the classical way is to determine a K factor. And that's because these are old machines. And in the old days, they couldn't measure, or these things wouldn't even work at the low ends where the Struhal number does some weird stuff. We characterize it from the low to the high. It does some nice things in the middle, weird stuff at the top, and weird stuff at the bottom. We characterize this meter throughout its entire range, and then we create, because of this industry, we create a solid K factor that would be accepted in the industry, and then we have in order a 5 breakpoint linearizer, if you will, to take care of those funny deviations at the low end, the middle, and the high end.
So you basically assume it's linear.
Well, no, we create it to be linear because what the customer wants, 4 to 20 milliamps for 0 to 100 CFM.
Okay.
And you don't get that with a wonky curve like that. So we characterize it and we cause it to be linear so that the output will be linear for the customer. And it's a pain in the butt because we have to characterize every flow rate. We characterize 10 points in this device, every 10%, and we then determine a transfer function. We could do a polynomial, or we're doing
Almost
it
like a
classical.
lookup table leap, and you can just
Yeah,
create
you
that
can do a
maps
lookup
one
table. Yeah, and a lookup table is a common way. They'll split it up into 255 individual lines, and they'll determine where they are and do y equals mx plus
And then
b
just do a
between them.
linear
Yeah.
relationship between those 2 points.
Yeah.
So one lookup table with 250 points and
Yeah.
then a slope essentially.
Yeah, between each one. But the community of folks who buy these, let's say, old timers, don't know that this isn't faithfully represented by a single K-factor. They in fact have lockout specs written in the system shall have a single K-factor, blah, 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 not even knowing that there's an improvement, like we got Teslas now.
Oh yeah, like don't use one K factor for everything on the slope. Like
Yeah.
use the right K factor.
Yeah.
That makes sense.
It's tough because when you bring out new technology, you break certain things, and the things you break are people's buying habits or lockout specs by engineers who wrote it in the 50s and 60s. So it's tough to get it well known.
And then just to kind of back up, so you're essentially going through every single flow meter we have, and then using LabVIEW to write code to take out as much of the errors as possible.
Yeah, the LabVIEW is the means to create the lookup table, if you will.
Yeah.
The means to characterize that.
To
To
get rid
some
of the
extent.
systematic error.
Yeah.
And then I'm assuming with some of the random error, you can just just have multiple data points and then just average it out.
Yeah, we do.
So,
Yeah.
cool.
And I was thinking George can explain the diffusivity. George has got it. Explain the diffusivity in this one,
All right, George.
because you can.
Okay.
Come here, take it and explain it. Because like this one you got it. I don't.
This is George. He's the head of sales, and he leads our diffusivity.
George is an engineer who happens to sell stuff.
Yes.
Yeah. So diffusivity is a measure of how fast molecules will propagate inside of other molecules. So essentially, you could think of flow, the size of the molecule. Is the smaller the molecule, the higher diffusivity it is. That's the relationship. So essentially, it is the speed at which the molecule bounces between other molecules, whether it's itself or a different gas, and essentially it's describing how fast the molecules travel without any kind of pressure or temperature or any kind of effects. Just it's simply a quality of the size of the molecule. So essentially, a small molecule will travel from here to here much faster than a large molecule.
And I'm thinking basically, if we have a room and we put in some, I don't know, some
Hydrogen.
gas and hydrogen into the room, the diffusivity is how long it takes for that hydrogen to be everywhere in the room.
Yeah,
essentially.
it is a function of the size, and essentially it describes how fast the molecule will
Cool.
will
And for
go from
whatever
one point to another
for
point.
whatever reason, smaller molecules have a higher diffusivity than
That's
larger
correct.
ones. Cool.
And
Thanks.
so
George.
it gets in the way of the measurement of the velocity.
Yes.
It goes to the velocity goes faster because the hydrogens move faster.
Yeah.
more diffuse.
So for this kind of meter, it's really important to set the diffusivity at the zero flow condition. And if you look at our manual, there is a step in there that describes how to essentially correct for diffusivity at zero flow. So
So
if
that's
you
what
have-
you do. You just go through, put it to zero flow, measure the diffusivity, and then put that into our flow meter, and you've corrected for it.
That
Problem
is-
solved.
Zero is really, really, really hard to create.
Yeah.
You have to have valves on each side. It's crazy hard. And nobody does zero right.
Yeah.
Zero doesn't exist.
Yeah.
That's funny.
So
yeah.
this
You're like, yeah, just go through it to zero, and you're like,
Yeah, this meter, we've had customers try it out with hydrogen, and the diffusivity is critical in those applications.
So you really have to get that right.
You have to get the setup proper.
Do you have any tips on how to get the diffusivity right, other than call you?
Essentially, our manual does a good job of describing that, but essentially you have to create a no-flow condition. You have to run through a series of buttons, and essentially what you're doing is you're having you're having the meter measure how fast the molecules propagate across from one side of the sensor to the other side of the sensor.
Yeah, so the meter has a built-in diffusivity correction algorithm.
So you
invoke
just set it
and
at
boom,
zero.
it's done.
Yeah, you basically put it into low flow condition, and the meter says, "Ooh, it looks to me like it's going at 1 meters per second."
Yeah.
But it's not. So
Yeah.
I'm just going to call 1 meter per second 0.
Yeah, something like that.
Something like that. Yeah. Cool. Thanks, George.
All right.